Alrighty, ladies and gentlemen, boys and girls, we are back with another one. Question 4 from the 2019 Calculus AB examination. And as you can see from your screen, we are dealing with a cylinder with what appears to be a volume of some sort of liquid. Okay, so let's see what's going on here. Maybe we can get it under 20 minutes. Let's see. A cylindrical barrel with a diameter of 2 feet, okay, cool, contains collected rainwater as shown in the figure above. The water drains out through a valve, not shown. There's some sort of valve down here where the water is leaving. At the bottom of the barrel. The rate of change of the height h of the water in the barrel with respect to time t is modeled by dht is equal to -1/10 root h, where h is measured in feet and t is measured in seconds. And then they do us a solid and tell us that the volume of a cylinder with radius r and height h is v equals pi r squared h. Well, our particular cylinder and the water within it doesn't just have some random r. It has a fixed radius of half of our diameter of 2. And so this volume here of our cylinder, or cylindrical volume of water, is going to be pi. The radius here is 1 times h, and the h is the thing that is going to be changing. So our volume, wherever we are, is just pi times whatever the height happens to be. Okay, so that'll kind of come into play. So question 1 says, find the rate of change of the volume of water in the barrel with respect to time when the height of the water is 4 feet. Indicate units of measure. Okay, so we've got related rates here. The volume is changing as the height changes. We know how the height is changing. We want to know how the volume is changing. Related rates, let's do this. Where's my scratch paper? Did I not pull one out? Oh, here we go. Okay. So again, in case you missed the intro, this is FRQ number 4, non-calculator section. FRQ number 4, exam year 2019. Let's do this. So part A is inquiring about the rate of change of the volume, otherwise known as dV dt, when t equals 4. Okay. Well, we just took a little bit of time to convince ourselves that the volume at any given moment is pi h because of this little relationship here. And so this is going to be equal to, let's go, derivative with respect to t of the volume, which we said is pi h, and we specifically want this when t equals 4. Okay, so we just need to differentiate on the right side and plug in a 4 and see what happens. Well, if we differentiate the right side, nothing happens with our pi because that's just a constant. The derivative of h with respect to t is dh dt. And so dv dt is equal to pi times dh dt, and luckily the problem gave us in the setup what this derivative is. So we'll plug that in. And we want pi. That's why this is messy. We want pi times dh dt, which we're told is -1/10 times the square root of h. I'm sorry, this should be h equals 4. This is h equals 4. Not when time is 4, but when the height is 4. When h equals 4, plug that in, we get pi times -1/10 times the square root of 4. And at this point, we can be done. Well, actually, no, we can't be done because we need it in terms of, to indicate units of measure. This will be a volume, which means cubic feet per second. Per second. Okay. If we did want to be nice to our reader, we could simplify that. Square root of 4 is 2. 2/10 is the same as 1/5, so this is negative pi fifths cubic feet per second is the rate at which our tank is draining, okay, or the volume is changing. And I guess if we want to be really precise, we will write a quick conclusion. Okay, so when, and again, every time you're not sure how to write a conclusion, go to the problem. Copy the language. So when the water when the height of the water is 4 feet, the rate of change of the volume of water with respect to time is negative pi fifths cubic feet per second. And we ask ourselves, does it make sense that the rate of change is negative? Of course it makes sense. The volume is decreasing because the water is draining out. All right, that was part A. Part B. When the height of the water is 3 feet, is the rate of change of the height of the water with respect to time increasing or decreasing? Explain your reasoning. I see words increasing and decreasing, and I'm thinking derivative. The question is, derivative of what? Well, is the rate of change increasing or decreasing? Is the rate of change of the height, is dh dt increasing or decreasing? So we're talking about the derivative of this rate. The derivative of dh dt. We're talking about the second derivative of h. Okay? And so we want to know, is dh or d squared h dt squared positive or negative? If it's positive, it tells us that the rate at which the rate is changing is increasing. If it's negative, then the rate is decreasing. So we are interested in the second derivative. The second derivative. So let's go and see if we can find that. So we want d squared h dt squared, and this will be equal to d dt of dh dt. So the derivative of dh dt, again, we know what dh dt is, so we'll plug that in. So the derivative of negative 1/10, let's call this h to the 1/2. And take the derivative. So this will be negative 1/10. The derivative of h to the 1/2 is 1/2 h to the negative 1/2, then we have to remember this is not just a variable. H itself is a function of t. The height is changing. So we need to chain rule and get dh dt. Some implicit differentiation going on here. Well, all right. Let's start to clean this up a little bit. We're going to get that this guy we can turn into, let's say, negative 1 over 20 times the square root of h. Just throwing that h to the negative 1/2 down below. The 2 and the 20, 2 and the 10 make 20. We got negative 1 up top. And then subbing in dh dt, the same old expression of negative 1/10 times the square root of h. And in a second, they asked at a specific point, but let's consider this expression. The second derivative, the rate at which our height is changing, regardless of what the height is, we can plug in anything for h here. This is a negative times a negative. It's always going to be positive, whether this is a 3 or a 17 or a 18.5. It does not matter, and that makes sense. If you consider your past experience watching things drain, and consider how the height changes as something drains, the closer you get to the bottom, the quicker the height is losing height. Okay? The rate at which the height is changing is increasing. Okay? Think of a bathtub. It's almost imperceptible at the beginning as the bathtub drains, but then as you get closer to being empty, it appears that the height is changing quicker. The rate is increasing of the rate of change of your height. Okay, so yeah, we can plug in the 3 here to show ourselves that for this particular case, that negative 1 over 20 root 3, because again, they're asking us at when the height is 3 times negative 1 times 10 root 3. And we actually see the h's cancel. Okay, so this is always going to be equal to positive 1 over 200, which is greater than 0. Okay. And so our conclusion here is when the height of the volume of water, or the height of the water, is 3 feet, the rate of change, the rate at which the height is changing, the rate of change of the height of water is increasing. And to explain your reasoning, our reasoning is because this is greater than 0. That's all she wrote. Oh, cut off some of that. We're okay, box it up, move on. Part C, third and final part. At time t equals 0 seconds, the height of the water is 5 feet. So they're giving us an initial condition here, 0, 5. All right. Use separation of variables to find an expression for h in terms of t. They want to know h of t. Okay, we know how h is changing, but we want to be able to figure out what is the height at any given time. And they're telling us to use separation of variables, so I'm thinking separable differentiable equation, and then integrate. So they give us this initial condition that time 0, the height is 5, which will come into play after we separate and integrate. But let's start with what we know. that the change in h with respect to t is equal to negative 1/10 times h to the 1/2. They tell us to separate variables, so let's go ahead and do that. We'll move the dt over here, and we'll move the h over here to be at home with the dh. And so we will have, we'll have h to the negative 1/2 dh is equal to negative 1/10 dt. Okay, divide both sides by h to the 1/2, or multiply both sides by h to the negative 1/2. And now we've separated our variables, and we can integrate on both sides. Integrate on both sides. And since this is just a power rule, this should be pretty simple. We'll get h to the 1/2, we need to multiply by 2. When we do anti-differentiation, because again, if we drop that down to get to our h to the negative 1/2, we need the 2 to cancel with the 1/2. On the right side, we get negative 1/10 t, and we keep our plus c on the right side. This is the solution. This is the general solution. And that would be fine if they were asking for the general solution, but they gave us a initial condition where we can actually find c. Now, you should stop at this point and solve for c. Okay? You could try to set this up for h and then solve for c at the end, but in the event that you made a mistake in that process and then got the incorrect value of c, you would lose that point. You get a point just for finding c. So let's find c right here by using this initial condition that at time 0, h is equal to 5. So we get that at time 0, h is equal to 5. And so we get that 2 root 5 is equal to c, and you will get a point for having that line. Okay, so now we will go through and actually find the h of t. So we have 2 times h to the 1/2 is equal to negative 1/10 t plus this newfound value of c of 2 root 5. Want to solve for h. Divide everything through by 2 to get that h to the 1/2 is equal to negative 1/20 t plus root 5. Just divided everything by 2. And then finally, if I want h by itself, I'm going to square everything. And so h of t, once you get rid of that 1/2 variable or exponent, you can write h of t. And heck no, we're not going to try to expand that out. We're just going to say that h of t is equal to negative 1/20 t plus root 5 squared. Box it up. Get on with your life. Okay, in terms of the points on this problem, starting from the top, let me just pull up the solution real quick. Un momento, por favor. Part A was a 2-pointer. So you got 1 point just for this correct derivative. That was 1. The second point was for actually having the correct value, so the correct specific derivative. So this conclusion was worth the second point. That was 2. The part B was also worth 2 points. No, I think it was worth 3 points. One sec. 3-pointer. How do they break it up? You've actually got a point just for this line right here. That was 1 point. You got a second point for your first point was actually a line higher. So actually this was 2 points wrapped up in one. You got 2 points, 1 point first for identifying this derivative, and then for identifying that the second derivative was this whole expression. And then your third point was for your conclusion. So that was 3. On the part C, the point breakdown was a point for separating your variables. So a point for separating your variables, a point for the correct antiderivatives, a point here, a point for C, and then a point for the correct expression of h of t. So 4 plus 3 plus 2, that's how you get full credit 9 out of 9 on FRQ number 4 from the 2019 AP exam. Parts 5 and 6 coming at you shortly. Here we go.